We are TruBalance Battery Management Solutions, and we have designed a lithium-ion battery pack and management system for a Formula electric race car. Our sponsor, SAE at UIC Motorsports, designs and builds Formula and Baja racing vehicles powered by combustion engines. This year, the organization has begun initial designs for their first electric-powered Formula car to compete in FSAE electric competitions. These competitions focus on static events that judge the build of the vehicle, as well as dynamic events that include endurance races on a track. Prior to these events, the vehicles must pass stringent technical and safety inspections. During a 2021 competition in Nevada, only 10% of the teams passed the electrical inspection, which is required to compete in any dynamic events. We are providing the team a safe, reliable, and scalable battery pack and battery management system to allow the team to successfully compete in all FSAE events. We provide safety through our adherence to all FSAE rules and regulations. Our management system has been proven reliable through testing to ensure accurate monitoring and control. And finally, we provide scalability through a modular design to allow the organization to easily expand the system based on their vehicle's current and future demands.
Our design and engineering requirements for the system were determined through our sponsor constraints, FSA rules and regulations, and SAE and IEEE standards. Our sponsor provided us with initial constraints of utilizing the 18650 lithium-ion cell packaging, a Reinhardt motor controller, and an axial flux MRAX motor. Additionally, our sponsor gave us a list of their most pressing needs and requirements in the system, which included safe operation, reliability, serviceability, and ease of diagnostics. We have designed a system that conforms to all FSA safety regulations, provides reliable operation based on our use of robust analog devices components, provides exceptional serviceability through our module design, and provides easy diagnostics with the help of our automatic fault detection and customized graphic user interface. During our initial market research, we came across our primary competitor, the Orion battery management system. These systems are widely used in FSAE events and provides teams an out-of-the-box solution to integrate directly into their vehicles. Although the team has the option to purchase the Orion system, they are limited by purchasing it based on the set number of series of cells without the option for expansion. We have provided the team with a solution with more customizable features built from the ground up. Our system allows easy battery scalability for future generations of our clients' vehicles. Plus, our system will benefit the team's static event scoring since more points are awarded for built systems over bought systems. And even with our more customizable solution, our system comes in a comparable, if even slightly better price.
Our battery design will incorporate cells configured into modules. Each module will be made up of Samsung 25R 18650 lithium-ion cells. These cells have a maximum of 4.2 volts and a 2.5 amp hour capacity. The module will be configured with 5 cells in parallel and 18 cells in series. This combination will provide a maximum of 75.6 volts, 12.5 amp hours of capacity, and a total energy per module of 810 watt hours.
A battery management system is built around integrated circuits provided by analog devices. The system provides accurate and real-time monitoring of the individual and overall parameters of our battery pack. This includes current, voltage, power, and temperature measurements as well as fault detection capabilities. These features maximize the lifetime of our battery cells and increase the usable capacity of our pack, allowing for maximum vehicle performance while ensuring safe and reliable operation. Our system utilizes isolated SPI for internal communication and is capable of controlling our external safety and operation circuitry that consists of a shutdown circuit and isolation relays. Our system utilizes a Arduino microcontroller, or DC2026C, as the main processor. This board is an Arduino-compatible system and comes with firmware libraries for battery management systems. DC2026 is also capable of decoding the isolated SPI communication when connected with a DC2792 communication board. With a dual-port isolated adapter implemented in the DC2792 board, our system allows for battery pack upgrade through the capability to daisy chain monitoring boards to the same communication line. This feature will also ensure a robust and long-distance communication between our system components.
We are utilizing a DC2350B board from Analog Devices to independently and accurately monitor 18 cells connected in series. Through the available GPIOs and incorporating a MUX expansion board, we can also provide temperature monitoring for all 18 cells. We are utilizing a DC2732 from Analog Devices to measure a real-time load side voltage, current, and power. This board incorporates a shunt resistor and is connected on the low side bus of the high voltage circuit. It also provides 2 high output GPIOs for an extra option in isolation relay control.
Our system utilizes 2 battery isolation contactors, one on each pole of the battery. These contactors are rated for 250 amps of continuous current and operate on a 12-volt coil. Control of the contactors is achieved through GPIO control of our dual MOSFET low-side driver circuits. This allows us to quickly and safely isolate the battery from the traction side of the vehicle. The shutdown circuit of our system is a predetermined combination of normally closed switches specified by FSAE rules. The shutdown circuit includes an inertia switch, a brake plausibility switch, a low voltage master switch, and a brake over travel switch. All of these devices are capable of interrupting the positive side of the low voltage circuit, effectively disconnecting power to the isolation relays when any of the individual switches are activated. Our system is designed with several overcurrent protection devices. The isolation relays are automatically opened if the current sensed by the 2732 is measured above a user-defined maximum operating value. Additionally, we have included 2 fuses in the high voltage circuit. One fuse is located on the positive bus, and the second fuse is built into the high voltage manual disconnect, which also serves as our service plug.
We have implemented a graphical user interface, GUI, using a Java-based environment called the processing. The GUI continuously scans and displays real-time data and fault codes of our battery pack. This GUI can serve as a diagnostic tool of the battery pack, as well as a ground-up software for further development of the system.
For our EXPO prototype, we implemented all of our management system and 1/5 of our module, that is 18 cells in series. The prototype is built on acrylic board to neatly combine our monitoring boards with the high voltage circuit and safety controls. The prototype allows us to demonstrate our monitoring of voltage, temperature, current, and power using the previously mentioned Analog Devices components. Next, we will demonstrate the functionality of our system through a series of demonstration videos.
The DC2350B board also allows us to perform passive cell balancing. During module charging only, each of the 18 cell segments can be independently discharged at 130 milliamps. That is done through the use of MOSFET-controlled resistive discharge circuits. Further developments can increase the discharge rate by changing out the discharge resistor or by adding supported auxiliary active balancing circuits. Cell discharging is directly controllable through our GUI. When charging mode is initiated, our system will automatically detect an out-of-balance condition, then charging will pause and balancing will initiate. In this demo, we are showing a manual control of the discharging feature through a clickable button in our GUI. Here we can see cell number 13 as it's discharging. You can clearly note the voltage reduction of cell number 13 compared to other cells.
For our prototype system, the ready switch is our low voltage master and our shutdown circuit. When ready is engaged, 12 volts is supplied to all the boards and monitoring and communication begin. To engage traction and charging mode, the red AMS switch is engaged. This sends a signal to the Arduino, which checks conditions of the system and closes the isolation relays if those conditions are met. We have also implemented fault detection to make our system diagnostics faster for the team. Detectable faults include high voltage open circuit and short circuit conditions, overcurrent in the high voltage system, over temperature, over voltage, and under voltage. When any of these faults are detected, they are displayed on the GUI and a fault light is illuminated through GPIO control. Additionally, faults will immediately deactivate the isolation relay circuits.
An open circuit is detected through comparison with the load side voltage sense. In this demo, we have left the manual disconnect plug uninstalled to simulate the open circuit. If no voltage is sensed on the load side once the isolation relay command has been sent, the isolation relays will be commanded open, the fault light will be illuminated, and the tractive mode will be made unavailable until the system is manually reset following an inspection.
A short circuit is detected through the use of our load side voltage sense circuit. If the system is turned on in ready mode and battery voltage is sensed on the load side without an AMS on command, the fault light will be illuminated along with the high voltage present warning light.
Our system monitors the cell temperatures and will automatically disable the tractive or charging systems in the event that any cell's temperature increases above the maximum allowed temperature.
When a current higher than our specified maximum is sensed, the system will react by commanding the isolation relays open. In this demo, we have set our current maximum to 2.7 amps. When the current drawn from the battery reaches 2.7 amps or greater, the system opens the isolation relays, illuminates the fault light, and records the fault in the GUI. Our system's fault reaction time, including this demo of an overcurrent condition, occurs in less than 720 milliseconds. That is the time from the moment a fault is detected to when no voltage is present at the load side of the isolation relays.
Initial testing of our battery cells in single and parallel combinations show how long we can supply a continuous current to assist the team in performance design. We will show that we can supply 25 amps of continuous current to the traction system for 30 minutes, an average time to complete the FSAE endurance event. This will help the team determine the final battery pack required to meet their performance goals. For this demo, we show full operation of our system and GUI. We used an electronic load to control our discharge of the system at 5 amps, which relates to 2 times the C rate of our 2500 milliamp hour cells. During the discharge, we can see the GUI actively monitoring module state of charge, the voltage and temperature of the individual cells, the current and power being supplied, and the energy remaining in the battery module. Evaluation of the data recorded during the test confirms our deliverable goals. Based on the linear relationship of C-rate discharge of the battery module, we're showing that the team can get a reliable 25 amps continuous discharge for 30 minutes.